This module is Module 3. It covers the measure phase of the DMAIC process.
I'm a certified Six Sigma Black Belt with the American Society of Quality, and I'll be conducting your training.
Some basic terms relevant to the measure phase are: a population refers to the entire set of data. A sample refers to a randomly selected data from a population, and it produces sample statistics that are used to infer conclusions about the population. This is inductive statistic or statistical inference, and it uses probability. Descriptive statistics only describe the data group without drawing any conclusions. Traditionally, populations use Greek letters and samples use letters, but literature is inconsistent. Your best bet to use context to determine if the data refers to a population or a sample. Descriptive statistics. The purpose of descriptive statistics is to present data in a way that will help with understanding. The following data was taken from a rod after machining and placed in a check sheet. The diagrams show the spread of the sample data, the shape of the sample data, the approximate center of the sample data. Distribution is the spread of data. Its spread is referred to as dispersion or variation and defined with range, variance, and standard deviation. And here we see the calculation for standard deviation for a population and for a sample size. The n minus 1 in the denominator of standard deviation for a sample is a correction factor for sample size. It's called an anti-biasing factor or a correction factor, and many of those come into play from statistics in the use of samples, in calculation of distribution, and in the calculation of distribution used in control charts that we'll cover later. Central tendency is a measure of the clustering of a distribution and a measure of its location. Central tendency is evaluated by the average or the mean. It's also evaluated by the median, which is the point where half the data is above and half of the data is below, and its mode, most frequently occurring value. Not all distributions have a mode. So in a set of numbers 3, 4, 4, 5, 6, 8, 18, 20, and 40, the mean is 12, the median is 6, and the mode is 4. Kurtosis refers to the overall peaking or flatness of the distribution, and skewness measures symmetry. Right skewed, the mean is right of the median is right of the mode. Left skewed is reversed. The central limit theorem states that the shape of a distribution of the mean of any population, regardless of the shape of the actual shape of the population, is approximately normal if the sample size is sufficiently large, usually around n greater than or equal to 30. The approximation improves as the sample size gets larger. So the larger the sample size, the smaller the standard deviation of the distribution of the mean. So the mean of the sample size equals the mean as sample size increases. And the error in that, the difference between the mean of the population and the mean of the sample is equal to the standard deviation of the sample means, which is equal to the population standard deviation over the square root of the number of samples. That's called the standard deviation of the sample mean, or the standard error of the mean. The central limit theorem is behind a lot of hypothesis testing, and you should begin to become familiar with it, but you need not necessarily have an in-depth understanding at the yellow belt level. In data collection, you want to make sure that the right data is collected. In other words, it's useful. Structure your data so that everyone understands what data is to be collected and why. This is operational definitions. Operational definitions Describe the data collection plan in enough detail that everyone is clear how to measure, who's going to measure, what instruments you'll use, what subgroups you'll take, what forms you use, and so on. Think about how you can sort and stratify data to provide clues to the vital problem factors. And the vital question in data collection is, what question do you want to answer? Check sheets and checklists are basic data collection tools. Surveys can be used to collect data. Surveys must be carefully designed to be effective. When you interviewing is a form of survey where you have an interview plan with questions to ask before you interview. You can use existing historical data. The data must be in a form you can use. You should verify, of course, that the data is still relevant, and you should know how and when the data was collected. Here we'll go over operational definitions a little more, and it's an important term. Edwards Deming was very big on operational definitions. He thought most of the problems in the world could be solved with sufficient operational definitions. And it's used in psychology, science, engineering, medicine, most any technical discipline. An operational definition is a sufficiently detailed description of a process, activity, or project term written to ensure understanding among the members of a group. So a lot of times I have project term there highlighted because many times in team meetings you'll talk about objectives and you'll use terms, and you'll want to make sure that everybody agrees what that term really means. For example, quality and better or good or excellent are all terms that need operational definitions. They remove ambiguity. Everyone has a consistent understanding. They provide a clear way to measure the characteristic. They make sure no matter who does the measuring, the results are consistent. So terms or processes or steps to be taken really need to sit down and have a definition that has enough detail that everyone that's involved understands and agrees to the definition. Again, another slide on operational definition. Look at it from another perspective. It's needed to make clear, precise instructions on how to make a particular measurement. Ensure common, consistent data collection and interpretation of results. To create an operational definition, the team discussion of the data to collect and the goal of the data, what question you're trying to answer for that data. Design a procedure for collection. Maximize use of visual guides and photos. You need the steps for the data collectors, how to take the measurements, what forms and instruments, how to record, what units. Test the definition or the plan out with those involved in developing the procedure. Then with those not in the procedure as a way to check it, and compare and adjust. And here's a typical chart or table for data collection for a plan. What to measure, what's the question to answer, what's the measure name, the data type, the tools to use, operational definition, words, formulas, what's the sampling plan, what's the collection method. This is kind of typical items that you'll find in a data collection plan. It will vary, of course, by situation. Again, we'll talk about continuous and attribute data. Variables data comes from measuring and has a continuum of possibilities. For example, a pin is 0.250 inches in diameter. Statistical distributions associated with variables or continuous data are typified by the normal distribution. Attributes data or discrete data, it cannot generate a continuum. Attributes data is discrete, employs statistical distributions such as Poisson or binomial, and those are yes or no or counts of data. Here's another look of the names of the different basic types of data. Quantitative, continuous, variable, like time, distance, location. Qualitative, or attribute, discrete, categorical. Pass, fail, yes, no. Short, medium, tall, which is ordinal attribute data. Nominal, which is no ranking at all, such as color, red, blue, green. That's forms of discrete data. A measurement of system analysis, MSA, determines if a measurement system is functioning properly and can generate accurate data that's repeatable and reproducible. Accuracy is the agreement of the measured value with the true value or an accepted reference value. The components of accuracy are bias, and that's the difference between the average value of all measurements and the true value. Linearity is how accurate your measurements are through the expected range of the measurements. It answers the question, does my gauge have the same accuracy for all sizes of objects being measured? Stability refers to the difference in the average measurements obtained, taken over time. A stable measurement system is one in which the variation is in statistical control, typically demonstrated with control charts. So stability, you take a measure at one time and it's stable if over time you continue to get the same measurement. Precision is the ability of the gauge to repeat, or the measurement device to repeat. A gauge can repeat an incorrect reading and be precise, but not accurate. Repeatability is the variation of measurements obtained when one operator uses the same gauge for measuring the identical characteristics of the same parts. Reproducibility is the variation in the average of measurements made by different operators using the same gauge when measuring identical characteristics of the same part. So you can be accurate and precise, which is the best. Precise but not accurate. You can be accurate but not precise, or not accurate or precise. Discrimination is the resolution of a measurement system capability to detect small changes in the characteristic measured. The rule of thumb on discrimination is to have a sensitivity of a gauge be 1/10 of the specification tolerance. That is, a 10-to-1 ratio between the tolerance range being measured and the gauge ability to repeat and discriminate. So if a part tolerance is 0.0005, total tolerance range of 0.001, the gauge should repeat and discriminate to 0.0001 inches. Precision to tolerance ratio is a measure of the capability of the measurement system. Reducing PTR improves measurement system. A precision to tolerance ratio of less than 0.10 is good, greater than 0.30 bad. Variation of measurement equals variation of product plus variation of measurement system. So the precision to tolerance ratio is 6 times the measurement system standard deviation, or some references use 5.15 times standard deviation of the measurement system over the upper spec limit minus the lower spec limit. Gauge R&R, gauge repeatability and reproducibility, is one type of measurement system analysis done to evaluate the performance of a measurement system. It quantifies the capabilities of a measurement instrument, estimating repeatability and reproducibility. Typically involves multiple appraisers measuring a series of items multiple times. Measurement systems consist of the following key elements: the measurement instrument, the appraisers or operators, the methodology, and the environment. Gauge repeatability and reproducibility studies determine how much of your observed process variation is due to the measurement system variation. Statistical software packages such as Minitab typically provide two methods for gauge R&R: an analysis of variance and the X and R bar methods. They break down the variation into three categories: part to part, repeatability, and reproducibility. And then the analysis of variance method goes a step further and breaks down reproducibility into its operator and operator by part components. So gauge R&R gives the components of variation due to the measurement system itself, the gauge R&R, due to repeatability or due to reproducibility, or due to the part-to-part variation. We want the part-to-part variation to be the biggest component. That indicates that we're actually measuring differences in the part, picking up the variation that we want, and not being victim to the variation that we don't want from the measurement system. So in this example output from a statistical analysis software package, the variation is from measurement system, the repeatability component, not the part-to-part variation. So this measurement system analysis would fail. We would want the part-to-part variation to be the largest component of variation. Now this is for continuous or attribute. This is for continuous or variable data. Now for attribute or discrete data such as good, bad, go, no go, we can do an attribute MSA, or often called a kappa study. Attribute gauge studies calculate the amount of bias and repeatability of a measurement system when the response is an attribute variable. So here we see a typical output from a software package such as Minitab. And we have agreement within appraiser, which is analogous to repeatability. Here we see operator 1 agrees with herself 80% of the time from trial to trial, and operators 2 and 3 were internally consistent only about 60% of the time. So that's a measure of repeatability. We also show here that the graph shows agreement between the appraiser and the expert opinion, or the base standard reference value. And we see the percent of agreement was about 70% with one and about 50% with the other two. So those would probably be considered pretty low values. Probably some training would be in order to see why the appraiser isn't matching the standard better.